Hello, good morning students once again. So here today we are going to start with your third chapter from syllabus, that is antenna overview. Look at the name of chapter. Intentionally I have written the name as antenna overview because a study of only one antenna is a huge part. For example, we have to study its construction, that's what's structure. Then we have to study its design, we have to simulate it, is it? If you want to, you can practically fabricate it, and then we have to learn the applications, is it? So every antenna, if I want to start with study of each and every antenna, it will take a lot of time, is it? So in our syllabus we cannot complete all those in detail, so that's why I have selected few antennas and put them into your third chapter, and that's why I'm giving the name as antenna overview. Right? We'll just check the overview of those antennas. For example, how it looks like, what are the applications, how can we design those, is it? Those things will be covered under this chapter. So as before starting with this antenna overview, we'll start with types of antenna, because we have covered this types of antenna part in your first chapter also, but still as an overview, or let me call it as an revision, let us start with the types of antenna. I'll write here types. Right. So what are the types of antenna? We have already studied the types of antenna. First type of antenna includes a general, that is wire antenna. Look at this, wire antenna. The second type is aperture, wire antenna, aperture antenna, then array antenna. Then fourth type that we have studied is microstrip. I hope you remember that, microstrip antenna. Then fifth we categorize as reflection antenna, is it? Then sixth is lens antenna. So those are roughly types of antenna. We have divided different antennas under this category, is it, in the first chapter. See, I am collecting those only. So now if I want to start with antenna theory, then I must understand the first type, that is wire antenna. So we'll start with wire antenna. We'll focus more and more on that wire antenna first, because if you understand simple wire antennas like dipole and monopole, like how they are radiating, how the current distribution is there on the monopole and dipole, obviously it will be very easy for you people to understand rest of the antennas, that aperture, array, microstrip, reflector and lens and whatever, is it? So we'll focus more on wire antennas, is it? So wire antenna, the name itself suggests it is just a wire. You bend the wire, fabricate an antenna. That's what it is. You curve the wire, you make your own antenna. That's what. So wire antenna includes only a structure of wire. You shape the wire with some different structure, it will be your different antenna. That's what it is. Now our job is to just check its radiation pattern and all. So before starting with those radiation pattern and all, entering into that world, let us discuss about this wire antennas. So let me write here as a title. It's not a title as such, but see, heading I will say, I will write here wire antenna. So wire antennas are again divided into three parts. See, the first part is linear wire antennas. Then see, what do you mean by that linear? Linear means it's general cases, that is dipole and monopole. Now, why they are called linear? I will tell you why it is particularly called linear wire antennas. Is it? Second is loop antennas. So this is very much general. Loop means start with something and end at the same point. Loop, is it? A circle is a simple loop. So like this loop antenna, let me give an example of a square loop, or maybe triangular, circular, whatever. Is it? So this loop antenna means loop wire antenna. That's what I'm talking about. The third type of antenna is helix. I'll write full name as helix antenna. Here, see what do you mean by that helix antenna? Wire is arranged in the form of helix. Is it? For example, you can imagine a spring, a wounded structure. Can you imagine an inductor, a wounded wire? This is what helix antenna is. Now, some people call it as an helical antenna. Is it? Some people refer it as helix, some people call it as a helical antenna. So roughly those are 1, 2 and 3 types of wire antennas. Is it? So wire antenna is a broad category. Under that I am classifying wire antenna as a linear wire antenna, loop antenna and helix antenna. See, the structure of helix antenna will be like this. I told you to imagine a spring, nothing else. That's what. Imagine an inductor. That's what helix antenna is, or helical antenna is. Loop antenna, look at this. It can be a square loop. Look at this. This is a square loop antenna. This is a circular loop antenna. The wire should form a loop. That's what. And linear, it's a general, see, dipole. Two poles are there and you connect a feed. Means provide a input signal. This is what. Or there must be a feed like this. Is it? This is simple dipole, this is simple monopole. So those come under linear wire antennas. Is it? So apart from that, in the first chapter we have studied aperture antenna, array antenna, microstrip, reflector and lens also. So aperture means, see, let me write here. What do you mean by aperture? Aperture antenna means generally we analyze or study aperture antennas with reference to horn antennas. Is it? Array is a broad form. It can be anything. Array of dipole, it can have array of monopole, it can be array of microstrip antennas. So array means basically what? More than one element. That's what the thing is, more than one element means array. So what do you mean by that microstrip, or how microstrip antenna will look like? It will look like a PCB. Is it? A planar structure. Yes. And what about the reflector and lens? You know, can you even imagine a dish? Yes, every time whenever I say reflector or lens antenna, you imagine a dish, the structure will look like that. How those different antennas will look like, how can we design those practical antenna, everything is included in this chapter called antenna overview. That's why I said it's just an overview. We are not going to discuss each and every antenna in detail, because study of every antenna refer to a different book. So obviously it's a large, very large area. Now, as we started with wire antennas, stuck to wire antennas. We'll discuss wire antennas first in detail. How a wire, a single wire or maybe a two wire transmission line will radiate, that we'll discuss. Okay, come to the wire antenna. Again, we have classified it as a linear, the loop and the helix. Now, so if I consider linear, let me write it here. If I consider linear, then this linear means what exactly? It can be a single wire or it can be a double wire. For example, this is a single wire. Yes, and it can radiate. I told you that. Now, you might have seen old radios. Your grandpa might have had this. They hold the radio, is it? They hold the transistor radio, and they, what they do, they start to, they try to tune that radio, and if it is not happening, then what they do, they just insert a single wire. That single wire will work as an antenna for that radio, is it? So that single wire is referred as a long wire linear antenna. Look at this, a small single piece of wire. I'm giving it a name as long wire linear antenna. Look at it. Now, okay, now it is okay, long wire, only long wire antenna, it's not a linear, because again, if I want to form linearity, I need to provide a ground over there, is it? So instead of unnecessarily increasing the confusion, I will conclude it with long wire antenna, is it? Now what do you mean by that linear again? Okay. See, I had a discussion about long wire antenna. Take a wire, and that single wire will radiate, single wire will receive the signal. It is what your long wire. Then what the hell I'm talking about this linear? Linear means what exactly? Linear means it should have a return path. For example, let me write here linear. It means there is a forward path and there is a reverse path. Can I say it is a two-wire transmission line? Look at this, two-wire transmission line. If you are calling it as a two-wire transmission line, then also it is okay, but basically two-wire transmission line is a linear antenna. Yes, it's a two-wire transmission line. Clearly means what? Linear antenna. Both are same. Every two-wire transmission line is your linear antenna. Here in a long wire antenna, what we had? We had only single wire. See, only single wire is there, but here two wires are there, so that's why those are called linear. Now what the meaning linear? Linear antenna or linear wire antenna should have one forward path and another is reverse path. In our electrical circuits or any electronic circuit, what we call this as? We call this as forward path and we call this as a reverse path. Is it? Reverse path, or what I can say, it is a zero potential, or what I can say, it is a ground or zero potential. Is it? Earth. Actually, earth is a pure electrical term. It's not good to use the word earth here. Is it? So let me round it. It's correct but not suitable here. Is it? So the reverse path or ground signal or zero potential is necessary if you want linear antennas. Agreed? Reverse path. I'll write here reverse path. So one forward and one reverse is mandatory. So now, as we have started with dipole, we come to the linearity. We come to the linear wire antennas. That's what two-wire transmission line. So as we have used that word transmission line, let's start our discussion with the transmission line itself. Right? So from transmission line or through transmission line, we'll turn towards the dipole. So let me draw the transmission line now. See, whenever the word comes transmission line, the first thing that come in our mind is what? It is Z0. Yes, whenever transmission line come in picture, we started thinking about Z0. So look at this. I am feeding this transmission line. See, I am feeding this transmission line means I am applying some signal to the transmission line. Look at this. This is what my signal that I have applied at the one end of the transmission line. And what is the Z0? This Z0 is a characteristics impedance. Is it? Now, what do you mean by that characteristics impedance? So we are not going to waste time on that. But let me tell you in one line that along the complete wire, you cut it anywhere, measure the current and voltage ratio, you will get some impedance, and that is what your characteristics impedance, and it will remain same throughout the line. Yes, that's what the actual property. If it is a characteristics impedance of a transmission line that I'm talking about, it has to be constant throughout the line, is it? So I'm just writing Z0. Now see, the transmission line is fed at the one end and it is open at the other end. Look at this, it is completely open. I'm not going to connect anything here, is it? Nothing is connected. It is happening. So at this end, for example, if I say this is terminal A and this is terminal B, then in between terminal A and terminal B, the impedance is infinite because they are completely open circuited. Is it? But what is our theory? Our theory is the impedance which is present at the output, we call it as load impedance ZL. Is that the impedance which is present at the output is my ZL. But for this structure, for this transmission line, what is value of ZL? Value of ZL is infinite. That is known because it is purely open circuit. Is it? Now, see, if I apply signal, the wave is incident, or let me call it as an I, incident signal. Is it? Or incident wave. Is it? The wave is inserted, that is what incident wave. And now basic rule of transmission line is known to everyone. When Z0 is not equals to ZL, that is characteristics impedance of a transmission line, if it is not matching with the load impedance that is connected to terminate the transmission line, that's what the condition. Then what happen? Then signal reflects. Yes, signal will get reflect. We have studied the same theory over there in maximum power transfer theorem, is it? In our circuit theory, what we have is maximum power transfer theorem. Maximum power from the input side to the output side will be delivered only when input impedance or the circuit impedance matches with the load impedance, is it? If it is matching, then only maximum power will be transferred from input to the output. If it is not matching, then obviously maximum power will not be transferred. Some power will be transferred, but I can't say it is a maximum. That's what the maximum power transfer theorem is in our circuit theory. Now, for us, for this transmission line, if Z0 is not equals to ZL, then the signal will get reflected. So as signal is reflecting, look at this, this is maximum ZL, that is impedance. Now we have two wire transmission line. Z0 is characteristics impedance, ZL is a terminating impedance. For time being it is infinite, or I can say maximum. And this distance between the transmission line, or what I can say is the space, is S. Is it? The spacing between the line is S, and some frequency that I have applied here. Is it? Now, as if I am applying some signal, then if S has to be very less than lambda, obviously then only transmission line will work fine. Is it? You have to satisfy this, na? Basic transmission line theory says that spacing between the wire, spacing between the line should be very less if I compare it with lambda. Then only it is called transmission line. Otherwise, we can't say it is a transmission line. Is it? Yes, and I am satisfying this because I want it as a transmission line. So I have satisfied this. The space S is very small as if I compare it with the lambda. Yes, it is satisfied, and now I can call it as a transmission line. Z0 is characteristics impedance. If it is not matching with ZL, the signal reflects. How much reflection will occur? How to find it? Yes, the reflection is measured in this. What is that? This is called reflection coefficient. This is called reflection coefficient. Tau. Some people call it as a tau signal. Is it? Now, what is that reflection coefficient? You remember electromagnetic theory, your EME subject. You recall that it is ZL minus Z0 divided by ZL plus Z0. Yes, that's what the theory we have studied. ZL minus Z0 divided by ZL plus 0, 0. This is what your reflection coefficient. Is it? Now, I want to find how much reflection is there, or what is the value of reflection coefficient if ZL is infinite. That's what I want to find. I'm interested in that. When ZL is infinite, what will be the reflection? Is it? Because I want to reach at the antenna, I have started with the transmission line. Where I want to conclude with? I want to conclude with the antenna. So that's why I'm doing this. Now see, if this is what tau is, divided by ZL, then ZL divided by ZL minus Z0 divided by ZL, ZL divided by ZL minus Z0 divided by ZL. What I did? I just divided by ZL. Then finally what I am getting, reflection is equals to, see, it is 1 minus Z0 divided by ZL. Oh, plus sign is there. Okay, 1 plus Z0 divided by ZL. Yes, that's what the condition I am getting. But see, what is the value of ZL? ZL is infinite. And what is the value of Z0? Generally 15, 75, 60, whatever. So it means the value of ZL is very, very greater as compared to Z0. So value of ZL is very, very higher than Z0, or what you can say is Z0 is very, very less than ZL. So the ratio Z0 divided by ZL will be approximately 0. See, Z0 is very small. Divide a small number with a very large number, obviously you will get approximate 0 value. Then if I put this approximation here in above equation, then what reflection coefficient you will get? You will get 1 divided by 1, it means 1. So reflection coefficient will be 1, and that reflection coefficient is 1. It means this is what maximum reflection, because we know that reflection coefficient has its value in between 0 to 1. See, it has a range bound, that is 0 to 1. And now for this transmission line, I am getting reflection coefficient is equals to 1. It means I am getting maximum reflection. Is it? Maximum reflection when, okay, let me write it here in words. Maximum reflection when ZL is equals to infinite. See, reflection is maximum. It means radiation must be minimum. So let me write, reflection is maximum means radiation is minimum. Yes, and that's what the criteria. ऐसा ही होता है, अगर रिफ्लेक्शन ज्यादा है तो रेडिएशन कम ही होगा, अगर रिफ्लेक्शन कम है तो रेडिएशन ज्यादा होगा. दैट्स व्हाट द थिंग इज. But now see, reflection is maximum, it is about 1, and I don't want that, because I want this transmission line to work as an antenna. ये transmission line antenna के काम करना चाहिए. So then what I need to do? I need to reduce that reflection and increase that radiation. See, once you reduce reflection, obviously radiation will increase. एक को कम करो दूसरा इंक्रीज हो जाता है ऑटोमेटिकली, देयर इज नो इशू. इज इट? लुक एट दिस, एक को इंक्रीज करो दूसरा कम ही हो जाता है. इज इट? एक को कम करो दूसरा बढ़ जाता है. दैट्स व्हाट द सिंपल थ्योरी इज. सो नाउ माय फोकस इज टू reduce the reflection. Is it? For the time being, it is maximum. When ZL is infinite, it is maximum. ZL is infinite, it means when line is open, the transmission line is open. then there is no radiation. Right. So as if transmission line is now open, it is not terminated at all, and I'm getting maximum reflection. There is no radiation at all. Now what to do to increase radiation? Okay. Now what I will do is, look at here. Let me draw the same transmission line again here. And now I will flare the transmission line. Just let me flare that. Flare means spread it like this. For example, let me have this. Let me flare it. Spread किया मैंने उसको with some angle. So obviously now in that case there will not be 100% reflection, is it? There will not be 100% reflection. Some reflections will be avoided, is it? So what I can say, if this is incident, look at this. This is forward path, and for this wave, this is the for return path. Look at this, forward path, return path, is it? For the current, some current will go in this direction. Obviously, if I draw a line, then it will be in this direction. Now reflections are reduced. Why? Because now at the end, here somewhere at the end, impedance is not infinite. I bend the wire. It means I am not providing infinite impedance. I am providing some that is finite impedance. And as if it is a finite impedance, it has to absorb some energy, is it? So one component is this, another component is this. Now see here, let me write it here. 100% reflection is not occurred. This is the first point. If you flare the transmission line, if you spread the transmission line, if you bend it, then there will not be 100% reflection, is it? So one thing is clear, 100% reflection is not there. It means what? Some, or what I can say, signal will get partially reflected. Partially reflected. Signal will get partially reflected. Is it? What is the conclusion? The conclusion is, if you flare it, reflection can be reduced. Is it? But see, reflection is reduced. Yes, this is what the conclusion. But the question is why? Why reflection will get reduced if you flare the transmission line? Now let me tell you why. Because see, if this is the incident wave, some signal is coming. Let me change the pen. Look at this. If this is what the actual signal, some will come in this direction, is it? Look at this, some will come in this direction. This is forward path, this is reverse path. Things are okay. See, I am not drawing any reflected wave yet. Reflected wave तो हमने draw किया ही नहीं अब तक, is it? I am just talking about the transmitted wave or the incident wave or the inserted wave. Now, if this is the actual current which is flowing, then let me draw its component. Look at this, one component is here, another component is there. Those are the vector components, is it? Like this, I have to draw the component of a reverse path. Reverse path के भी हम component draw कर लेते हैं यहाँ पे. This is what? Now look at this. This component, okay, let me change the pen. This component and this component, now they will cancel each other. Because see, one is going in forward direction and another one is going exactly opposite to that. 180 degree phase shift, exact opposite. So obviously they will cancel each other. This will cancel this. But what about remaining component? So this component and this component will get added. Yes, that's what I wanted to tell you. Two components which are in vertical direction, they will get added. So as if two components are now get added, it means signal strength increases, signal can go into the air, signal can detach itself from the wire, signal has an ability to detach from the wire, and it can go into the air. Is it? Why it is happening? Because one component will get added, one current component is added, and then the strength increases. Now if strength increases, obviously it gains the ability to go out from the wire, to detach from the wire, and that's why when you flare it, obviously it will radiate and the reflection will be minimized. But now see, I didn't say this is antenna yet, because if I want efficient radiation, then do one thing. That's what your first transmission line, then you flare it, and now what do? You flare it 90-degree. Let me draw the another diagram. Look at this. You flare the transmission line fully. You flare the transmission line fully. Look at this. Here I have feed. Look at this. Current components which are adding are those components. Yes, those are the components which will get added, and rest of the components, that is second one, that's what they got cancelled. Is it? Now if you think about right hand thumb rule, I will write here right hand thumb rule. Now what right hand thumb rule says, if current is there in this direction from the conductor, then what about magnetic field? Magnetic field will be like this. Is it? Look at this. This is what the magnetic field. For example, you imagine this pen. If this is the direction of current, look at this, current is going up. Yes, from this conductor current is going up, then magnetic field will be like this. Look at this. Yes, this is what the magnetic field is. I hope it is visible. Let me check. Yes, so this is what my magnetic field is, it around the conductor. Yes, now this structure is called dipole. Why? Because when you flare the transmission line at 90-degree, it will radiate efficiently. Is it? Let me write, when you flare wires by 90-degree, then it radiates efficiently. So that efficient radiator is given a separate name, and that name is dipole. So this is what actually dipole is. Agreed? Yes, we started with the transmission line, we started with the linear wires, and then finally we reach towards the diode. Now I know what is diode. इसको हम dipole. Suddenly I entered into the circuit theory now. But the question is still unanswered, that how the waves get detached from the dipole. Yes, that's what it is. See, I said you flare it by 90-degree, waves will get detached from the dipole, waves will get radiated in the air. Yes, everything is fine, but how is the question? Look at this. How? Waves dipole से detach कैसे होते हैं? How? So now we will answer that question, how the waves will get detached. What we need is a separate page for that to understand the dipole clearly. Now look at here. Can I draw? Yes, I have line here. Let me draw a line. Okay, that's quite okay. I'll draw another line. One line. Okay, another line. It's quite okay. Now look at this. This is what my dipoles. The transmission line is flared with 90 degree. Is it? And look at this. This is what my input signal that I have provided. Intentionally, I am drawing that input signal in very large form. Okay, sorry, here. So what is this? This is what my input signal is, and this is dipole. So input signal is fed to the dipole, and now look at this. What is there on x-axis? Obviously, it is a period, time period. Yes, time period t. Now, during positive half cycle, we'll start with the basic second year theory. What will happen during positive half cycle? What will happen during negative half cycle? Yes, we'll start with that point. Now, sorry, nothing. Yes, it's gone. Now, look at this. Let me change the pen. And if I say this is a 0, and if this is t by 2, and if this is t, then how much is that? It is t divided by 4. And now input is increasing. Look at this, input is increasing. So obviously input is increasing. What is the positive hand? This is positive hand. This is negative hand of a dipole. You can say negative arm of a dipole. Is it negative pole of a dipole? Whatever the word you use. Now what will happen in that case? In that case, look at this. Electric field will travel in this direction, from positive wall to the negative wall, from positive hand to the negative hand. That is from positive arm to the negative arm, positive pole to the negative pole. See, the words are different, but the meaning is same. Now look at this. This is what happening. Let me draw the thirds also. Look at this. Okay. Look at the direction. It is purely downwards. It is completely downwards. Now, when it is happening during the period from 0 to t by 4. Look at this, during that period. Is that? So, during the period of 0 to t by 4, let me write from period of 0 to t by 4. Is it? The distance covered by the electric field is it's not happening. Yes, the distance covered, this distance I'm talking about. Look at this distance and this distance. Look at that distance, that much distance is covered by the electric field. So how much that distance is? It is lambda by 4 during the period of t by 4. Look at this, during the period t by 4, distance covered will be lambda by 4. Is it? But look at the input wave. What is happening after the period t by 4? After the period t by 4, input signal is decreasing. Is it? See, I have considered pure sine wave. Is it? So we are thinking about pure sine wave. Now, if it is a pure sine wave, then at the time of t by 4, after that it will start decreasing. So let me draw another dipole. Look at this. Okay, now this is okay. It is quite linear. Yes, and here somewhere I am applying input voltage, and now let me draw the sine wave once again. Is it? Let me draw the sine wave, positive, negative, this. Okay, how much period we are finished with? We are finished with t by 4, and now input is decreasing. Look at this, input is decreasing. So as if now input is decreasing, then what will happen? The poles will get reversed. The electric field direction will get reversed, because during the period 0 to t by 4, it is increasing signal. Now from t by 4 to t by 2, from this point I am talking about, is it? From t by 4 to t by 2, what will happen? Input is decreasing. So the electric field component's direction has to be reverse biased. Look at this. This is what this is now, complete reverse bias. Look at this. Purely reverse direction. Okay, let me finish this with sorry. Yes, this is what a pure reverse direction during t by 4 to t by 2. Now the question is, see, I have electric field lines during the period t by 4 to t by 2. Look at this, t by 4 to t by 2. Yes, within that period हमारे पास ये waves है. This is what electric signal we are having. Is it? तो पहले के electric fields कहाँ गए? Is it? What happened to them? Is it? It means from 0 to t by 4 यहाँ के waveforms कहाँ गए? 0 to t by 4 यहाँ के lines कहाँ गए? Where are they? Yes, they are here and we need to draw them. Look at this. But look at the direction. The direction is now will be as it is. Will be as it is. I need some space, so that's why I'll rub that. Yes, I don't want this. Even I can't rub that. Yes, so let me draw these transmission lines. Look at this one. Just because my drawing is not that much good, and look at this, the direction will remain same. Here also I have the same direction. Yes, this is what the direction will remain same as it is it? So this is the view. Actually 1, 2, 3, 4, 5 and 6 electric field lines I have. Is it? Look at this, 1, 2, 3 belongs to, look at this, 1, 2, 3. These 3 belongs to the period t by 4 to t by 2. Is it? And 4, 5, 6, those belongs to the period 0 to t by 4. Is it? And now my input signal exactly reaches at this point. The first cycle will completed. This is what the first cycle, it's get complete. Now what should happen when input signal reaches exactly at the 0, that is V in reaches to 0? At that point what should happen? Is it? So till now, when it starts from 0, it go to maximum. From maximum again it goes to 0. And now when it reaches to 0, when it reaches to this point, then obviously input voltage is 0. There means there should not be any positive pole and there should not be any negative pole. Positive negative ऐसा तो पोल कोई रहेगा नहीं. There will be complete zero bias. Both poles will remain at the same potential. Now what will happen to those lines now? तब इनका क्या होगा? अगर इनपुट ये 0 पे स्टैंड रहेगा तब इन लाइंस का होगा क्या? Yes, I will draw कि तब क्या होगा. So when input signal reaches exactly at 0, then हमारे जो लाइन्स है इलेक्ट्रिक फील्ड लाइन दैट इज 1 2 3 4 5 6, व्हाट विल हैपन टू देम? इनका क्या होगा? हाउ दे विल सस्टेन? अब इनको तो कोई बेस ही नहीं रहा, इज इट? सो देयर इज नो बेस फॉर 1 2 3 4 5 6 इलेक्ट्रिक फील्ड लाइन्स. नाउ हाउ दे विल manage, how they will survive? They will survive by creating their own loops, is it? And this is what a complete electric field. I'm not talking about the line now, I'm talking about the electric field, a complete electric field. Let me draw it here. Okay, and for that again I have to draw a dipole, and here it is. And here input voltage now goes to maximum and now it goes to 0 at this point I'm talking about, is it? At exactly t by 2, is it? Now here what will happen? These two lines, is it, 1 2 3 4 5 6, will get combined with each other like okay, let me use this pen. Like line number 4 will get combined with 1. Look at this, and it will form a structure like this. 2 will get combined with 5, is it? And 6 will get combined with 3. Like this they form a loop. Let me draw those loops separately here, is it? And look at this, they will create a structure like apple. कुछ इस तरह से वो लाइंस कंबाइन होते दिखाई पड़ेंगे हम लोगों को, एंड दैट्स व्हाट, लुक एट दिस, those lines will get combined, that is they form a loop, and that will be our complete electric field. Yes, and at t is equals to t by 2, this wave is detached from the dipole, is it? This is how the wave is detached from the dipole when input signal passes from 0 to t by 2. One half cycle, that is one blow, and the balloon will get detached from, is it? Even in your childhood you have played that kind of games, is it? What do you do? You create a foam of a soap and then you blow like this. First half cycle, one balloon goes out. Second half cycle, again one balloon goes out. Like this, a electric field form a loop and it will get detached from the dipole. And this is how this input signal will create balloons of the shape like this, is it? Now got the answer how dipole will radiate the signal from or by itself. Yes, this is the theory behind that. Right. So this is most important thing. And now, as if we have started with the diol and how, dipole, and dipole is now started detaching signals, we need to understand its radiation pattern also. Is it? So let me check whether I can show you a radiation pattern of dipole. Just let me check. So here we, this is dipole. As I said, this is how wave will get detached from the dipole, and the waves will get radiated into the space. So look at this dipole. Now why it is called dipole? Because it has two poles. I said na, it is positive and one is negative. Why the two wires or why two poles are needed? Because it's a linear type of antenna. In linear antenna, one is forward, another one is reverse, and it is mandatory. Is it? So when you flare that transmission line by 90-degree, they form a dipole. Now the question is, how much the length should be there? Everything is depend on that length. Length means this I'm talking about. Look at this L. What should be the length of dipole for getting efficient radiation? Is it? So now there are so many options. If you keep L is equals to lambda, you will get radiation, but radiation pattern will be different. If you get, or if you keep L is equals to lambda by 2, you will get radiation, you will get efficient radiation, but the radiation pattern will be slightly different than L is equals to lambda. Is it? So like this, lambda by 2 means 0.5. If I can say lambda is equals to 1, then L is equals to 1, L is equals to 0.5 of lambda, whatever. Is it? Some people use that notation. Is it? I use lambda, they use 1 lambda. If I am using lambda by 2, they use 0.5 of lambda. Is it? It's completely on your convenience how you are taking it. So length of the dipole decides its radiation pattern. So whenever a simple dipole is considered, by default people consider dipole length is lambda by 2. जब भी कोई आपको बोलेगा कि think about dipole, tell me about dipole, you tell everything about dipole's length is equals to lambda by 2. lambda by 2 का ही dipole हमेशा हम by default consider करते हैं. Is it? What it is called? Half wavelength dipole. Half wave dipole. What is the actual or technical full name? It is a half wavelength dipole. Half wavelength means lambda by 2. मतलब dipole का जो length होता है that should be lambda by 2. That is what half length dipole. Now come to its radiation pattern. We know how the waves get detached. Now radiation pattern, let me show if it is possible. Yes. Look at this. This is how a radiation pattern of a dipole of lambda by 2. Lambda by 2 dipole का ये radiation pattern है. Look at this. Isn't it looks like a donut shape? Yes, it is a donut shape. Now the shape will be different if I change the length. Look at here at the corner. I have opened that animation in photos and look at the corner. Look at this. I hope it is visible. Now dipole underscore 0.5 means 0.5 lambda. It means lambda by 2. Is it? Now let me show you the next image of a radiation pattern of a dipole of lambda. Is it? Length is equals to lambda. See, now the length is not lambda by 2. The length is exactly equals to lambda. And look at the radiation pattern. Yes, it is still donut. Is it? It is still donut, but the width is different. Is it? It's on us whether you are taking it as a width or the height. Height of the radiation pattern is quite different when L is equals to lambda. And what is the previous case? Look at the height or look at the width. It is less when it is lambda by 2. Now see here, if it is lambda by 2, then the width is quite less Let me increase the length. Look at this, it is larger now. Let me further increase the length. Now look at this, it is 1.5 lambda. Then the radiation pattern is something purely different, is it? Now look at this. This is again a dipole with 1.25 lambda. Look at this. This is a dipole radiation pattern with 2 lambda. Like this, the radiation pattern of a dipole is purely depend on what? It's purely depend on its length. Is it? So this is how it's all about dipole. Now the question is, how can I design the dipole? Is there any way, or I think it's always better to start design of all the antenna in a single lecture, because if I start design of dipole in this lecture itself, again there will be confusion regarding monopole design, is it? So that's why instead of having design here in this lecture, we'll cover the design in different lecture, is it? So probably I think we are done with the discussion about the diode, which I feel that much is sufficient for this chapter, is it? Maybe in next chapter we'll start with some other antenna, is it? Other means definitely we'll start with monopole, because now I know the basics of dipole. We can start with monopole then. Yes, till then, thanks a lot.